Alright, November 28th. Alright, let's do this. Was not able to do it last night because I need to return a book. And it turns out the library near where I live closed down for renovation. Alright, let's do this. Minimum obstacle removal to reach corner. You're given a 0 index to the integer array grid m by n. 0 is empty cell, 1 is obstacle. You may move up, down, left or right from and to any empty cell. Return the minimum number of obstacles to remove so you can move from the upper left to the lower right corner. So the first one we need to remove 2. Minimum number to remove. This is 0, right? You can just go. And we've done this before. I don't remember. We start from a point. The usual way of doing this is minimum number to remove. So we don't really care about the shortest distance, right? What we care about is the minimum number to remove so that I can reach. So I can, definitely try it, see if we can reach. But if we try it and then we cannot reach, then what? Like here, right? You cannot reach, but you have multiple that you can potentially remove. Or you can think of this problem as you have a couple of cliques, right? And you want to know what's the minimum number of steps and the minimum number of edges that you need to create in order to connect them, right? That's another way to think about this. So, okay, let's say we get those cliques out. Have one, have two, have multiple out, okay? And then the question is, given the two, how do we know the minimum to kind of break through? Interesting. I think. So we have some clique here, we have some clique here, and then in between we have some obstacles. Doesn't matter, right? So if we want to break through, what we need to find is kind of the shortest distance, right? To get through to these two. How do we find that? No idea. What? I was able to do it last time by myself. And I have no idea now. Morning. That was easy. I didn't do it last night, so I have to do it today. How was your sleep? How you feel? Happy Thanksgiving. And they put a difficult problem, and seems like I did this before on my own, but I have zero clue at the moment. Oh! We have light. The library will be closed until after Christmas. I have some books on hold.
Why?
Renovation. From November 18th to December 28th. And I have some books on hold and it's automatically routed to Bellevue. But I just realized Kirkland is closer, so I changed most of them to Kirkland. But I have one book already in transit, so that one we have to go to Bellevue to get it.
And because of the power outage?
I do not know. Not sure if it's planned or the power outage causes make them feel like, you know what, that's a good excuse. Let's just take advantage of this. I'm actually gonna go there. I think they had a plan. They wanted to renovate, but they couldn't find a good excuse. And then the power outage happened, like a perfectly timed power outage. We're just gonna take advantage of this and then keep rolling. Yeah. Dear me, how do you do this? Okay, so m times n. So maybe we can dp this. Okay, how do you want to dp this? I say, wait, what do you mean by dp this, right? Just can you reach the end? Okay, so starting from a node, we say, can you reach the end? All right, and then we will remove one and say, can we reach the end? I say no. Can you remove another one? So yeah, let's remove one. No, that doesn't feel right. No, that doesn't feel right. I still think maybe it's the distance idea. The so-called, Hamilton distance. Like along the edges. Because if we are blocked, we have one click and another click, if we're blocked, like from one cell to the other cell, right, you just either go this way, right? That's the shortest distance to move from one to the other. Of course, you can also go from here, right? But essentially, what we want to find is among these and among these, what is the shortest distance between a node, right? Between a cell to this cell. So in this case, the shortest distance, like you can say from here to here, that's a 0, 0, right? So we on one side we have 0, 0. On the other side we have 0, 1. There's a 1, 2, right? 1, 2, and 2, 2. So we find the shortest distance between the two. So this shortest distance between these two is 3. Well, we are doing, that's 3 or, because here, right, 0, 0, this is a 1, 2. So you need to go 1 down and go 1. How to find the shortest distance between these two? Like how many times do you just move right and then move down, right? Because that's the only two ways you can go. Move right and move down. Exactly. We just move right and move down. And this should equal to 2 because, you know, yeah, if we just say everything can have to move right and move down. That's the only way for you to reach. So move right, you get 2 moves, right? And then move down, you get holy guacamole. That is cold. We don't need to reach it. We just need to move it such that one of the index is the same and the other is missing by one. So in this case, one of the index is the same. So we move down 0 to 1, that's 1. The other missing by a 1 is 1. So we can say we have x1, x2, x1, y1, and the other is x2, y2. So what we want to do is just absolute, say x1 minus x2 plus y1 minus y2 minus 1. I think that's the formula, right? So in this case, it's 1 plus 1. So this is 2. This is going to be 1. No, this is going to be 2 plus 1 is going to be 3. So the answer is 2. Now that's getting everything from here to everything from here. All right? So you have a clique that includes 0, 0. And you might have multiple other cliques inside. And you have a clique that's at the end. Then you need to choose which cliques to go with. Still doesn't seem right to me. I mean, if we can find the shortest distance between these two cliques, that would be good. Like we know the shortest distance between these two, these two, these two, these two. So essentially, we turn these into nodes, right? And then we turn these into, we can say this to this, like we will cause you 2, and yeah, will cause you, this will cause you, this will cause you. Like you have weights, then you can Dijkstra this to find out, right? You can Dijkstra this to find out. Okay. That is a solvable problem. Now, how do we find the shortest distance between any two cliques? How? I'm asking you. And it's going to be, you get all the cliques out, which I just think it's going to be Okay, the pairwise comparison. Pairwise comparison. Pairwise comparison. Exactly. We do pairwise comparison. So we go through I and j, right? Each one we compute the distance between the two. If this is no obstacles, if I can reach, then distance is 0, right? If I can reach, distance is 0. If I cannot reach, let's say from here to here, if I cannot reach, no, from here to here, hold on, I think we might have some idea. Okay, we can run through this union find. Okay, so we group them together, and then we run again from each node, from each cell. Wait, hold on. It doesn't feel right. Let me think again. So from this to this. How do you find the shortest distance exactly? You do pairwise comparison. Yeah, you do pairwise comparison. You find the first click, right? You find the first click. You get everybody in the first click, second click, right? Third click. So everybody compared to everybody else. What's the runtime for this? I think that runtime is too much because you'll go through everything twice. Not twice, because you go this to this, this to this, this to this, right? And the second one you have to go through everything. Yeah, that's OM squared, N squared. Yeah, it doesn't sound like it can make a good difference. Okay, well, what else can you think about? All right, the only way to completely block is if you have obstacles that cut off an entire, right? It can cut off the entire column, right? Entire row, or that you have to reach from end to end. That's the only way for you to block something. Which means you have to reach at least. Yeah, this also doesn't block. This doesn't block. This doesn't block. But in order to block, you go this way. That's not gonna block, right? That is not gonna block. You can go. So you have something like go this. That's how you block. You go something like this. And that's how you block, right? I like the other idea of Dijkstra, but I need to develop this idea more. Well, the Dijkstra idea is you start from here. Okay. You'll go here and find out to reach this, so this cell costs you 1. Right, and this cell costs you 2. This cell costs you 1. And from here, yeah, it is going down, this cell costs you 2. So, and this cell costs you 2. This cell costs you 2. This cell costs you 3. 1, 2, 3, right? And this cell will cost you 3. This cell will cost you 2 again. So Dijkstra. So instead of seeing these as obstacles, you're seeing these as extra weight in the okay, start from here. Going here, you just cost you 1. Right, and then this goes here, it costs you 1 as well. And you just keep track of the total, you keep track of the total weight. And of course you go here, the cost is 0. So if you go Dijkstra, so each one start and then you comparing, right? Comparing the weights. And okay, this way is so you go here. From here, again, you have these, and you have visited, so you don't go back. Wait, do we do that? You don't go back, right? Yeah, you don't go back. What's the point of going back? So you don't go back. Yeah, you don't go backwards. Because if you go backwards, I mean, the whole point of this exercise is to go from 0, 0 to n minus 1, minus 1 with the minimum steps, or yeah, with minimum costs. It's just every time you go through a obstacle that will cost you 1. And you cannot go back. So yeah, in this case, I already visited. And then if I try to visit the next one, it cannot be visited before. And in this case, yeah, so I'll go down because this one has lower. Okay. Alright, and we'll go down. So we'll come here, and now we'll come here, and we'll come here, and I'll come here, I'll come here, here, yeah. Maybe Dijkstra will work, honestly. Maybe it'll work. So how do you do Dijkstra again? You do Dijkstra by, you start with something, and then you have a priority queue, right? You'll have your minimum cost to reach each cell. Initially, you set everybody to maximum, and then you go, and then when you hit the cell, and then you check if it's equal to. If it's not equal to, you pop the priority queue, and once you pop the priority queue, you get the next one out. Then the next one out, you look through, you find a cell that you haven't been there before, and you say, if I reach this cell, what is my cost, right? And then what is my cost? right? And then and then you have a cost, and then you compare, right, to reach this, compared to the cost. I have small. Okay, let's try it, right? Let's try it. Let's just kind of rethink this problem. And also practice Dijkstra. I haven't touched it for a while. Alright, so for Dijkstra to work, first of all, what we need is... What do we need for Dijkstra? We need a priority queue. We need this. What else? We need main costs. Oh. Enjoy. 10 to the 5th. We can do 10 to the 6th. Okay, so that's the preparation. And you'll put your thing in. Oh, and scene. Ooh. How do you do scene? You might as well compute it. Right, you might as well compute it. Yeah, I think it'll be easier just to compute it. Okay. What else? We still need 2. One will be yes, and the other will be yes. So position, 1D position, and steps. Costs. Okay. All right. We'll say int. Oh, I can use costs. So it's just smaller than max. That means we've seen it before. Oh, if it's the same, then we don't do it. Right? It has to be smaller. Yeah. Okay. So we say q.add. It's gonna be 0, right? 0 and 0. Okay, we start with 0 cost. All right. Yeah. Can do this. Q element q.poll. if min costs element 0 is not equal to element 1, continue, right? Because these two has to match. All right, so once we are done, then we can say I shall be element 0 divided by n mod n. Alright, we have ij. Now we can go to 4 directions, which we'll also define here. Alright, now we can say for okay. Okay, so we can say the current cost, new cost, right, shall equal to element 1 plus grid nij is equal to 1, right? Yeah. If it's equal to 1, that's going to be 1, otherwise it's going to be 0. And if new cost is smaller than min costs nij. Let's say min costs nij, the new cost, and q dot add new ni times plus nj, right? And new cost. Oh, int new index times n plus n nj. Yeah, my bad. This is wrong. Should be new index. Okay, so once we're done, we just need to return min costs n minus 1 times n plus n minus 1. That sounds right? Oh, I forgot to do that. My bad. Comparator. Oh. Oh shoot. Ah, my bad. Should be 1, right? Oh, that is hilarious. That is absolutely hilarious. Okay. Something is not right. Something is not right. Hmm. Oh. Oh. My bad. I forgot to do that. Okay. Alright, now let's try. Alright. I think that's a good sign. Consider this Dijkstra problem. Each time the goal is to find the minimum cost going from 0, 0 to n minus 1. n minus 1, n minus 1. Alright, this is the goal. And each time we pass through an obstacle, the cost increments by 1. I don't remember. What's the, I think, number of nodes? I think it's something like this. I think it's number of nodes, a log number of edges. Or maybe number of edges log number of nodes. I don't remember, but something to this effect. I've been very sloppy in this type of thing. Alright, let's see. Yep, that's exactly the case. So last time was Python. That was in 2022. Wow. So well, yeah, we solved it. So that's good. Is this the best solution? I'm not sure. Dijkstra. Yep, that is correct. Let's see. Dijkstra minimum obstacles. Yeah. Do that. assign, it's good. We do that. Kill, okay, that's good. Add new main obstacle, this two, not empty, get a current. If row, then we return obstacles. Maybe that can make it faster. And then we do directions. Is valid. So stall, we add. That's true. I think it has one more step. Basically, the first time we reach is always going to be the smaller. That is true. I don't know why I didn't do that. We can say if, right, ni is equal to -1 and j is equal to n minus 1. Or, not here, my bad, it's here. If element 0 is equal to m minus 1 times n plus n minus 1. Oh, and just m times n will return element 1. Early exit. I think that's probably exactly what I did before. Yeah, I didn't do the early exit. That was kind of an issue. Okay, that's that. So what else? BFS. Oh, BFS 1 0 0 1 BFS. Oh, we add empty cells to the front of the deck and sell it also to the back. We'll pop the top cell in the deck and explore its neighbors. All empty neighbors goes to the front, while others go to the bottom of their obstacle count. While others go to the bottom, where their obstacle count increment by 1. Okay, so let's see this. So this should be 1, right? There's nowhere to go. Yeah, so you pop the top, and then you go through, you just don't put anything in because there's no free cells, and then they have all been added. So you just pick one of them. So when you go, it's gonna be 1. Oh, it's gonna be 2. That's it. No way. 0, 1 BFS. Huh. Cells are processed increasing order of costs. Yeah, this just means once you hit, everyone has a current cost, right? This is just the same as Dijkstra, I feel. This is the same as Dijkstra, because you're actually ordering which one to go first. That's what Dijkstra does, right? Dijkstra orders which one you go first, but it orders this way by sorting them, priority queue, right? But here we say we don't really care. We always go the free ones first, because the cost to free ones is always 0, and the cost to the other one is always 1. But would it be possible that? Yes, that's the reason why it works. Is the cost is constant. The free ones always cost 0, so you can just put them in the front, because it will not make, because the current cell you're visiting always has the lowest cost globally so far. And the next one, if it's a free cell, that means the cost is 0, so you can always put it at the front. Doesn't matter. If it's not, then the cost will increment, so you have to put it in the back, right? You have to put a cost. If I put it in the back, and when you put it in the back, because the current is always the smallest, and each time you visit, it always costs +1, so you can always put it at the back. It's guaranteed that it is not smaller than any of the previously visited ones. So it is essentially a BFS, essentially a Dijkstra. Okay, so we can do that. We still have capacity, don't we? We do. We do have capacity, and then we're gonna do this. Alright, and in this case, since we are so this is from the official solution, which uses 0, 1 BFS. It is essentially Dijkstra, but since there are only 2 weights for 2 costs, right? 2 costs for any edges, we can simplify the priority queue step by always putting the 0 cost neighbor at the front of the queue, and the 1 cost neighbor at the end of the queue. This will guarantee that the queue is always sorted. Without having to go through priority queue. And of course, without priority queue, it's much smaller. So you got this is going to be array deck. Call Polytech. Don't need any of this. Main costs, fill, q dot add. Yeah. So here is the thing, right? The new cost. We need to decide if we want to put it, right? Okay, so it's if it's a 0, the new cost is 0, then we'll put it at the front. If the new cost is not 0, then we always put it back. And if we're doing that, do we even need to check? Yeah, we have a new cost. Yep. We still do this. And here is what we change. Then we say if new cost is equal to element 1. Oh, actually no, we can just go with what would be the best way to do this? We can say if it's 1. Okay. If grid and element 1 plus 1 smaller than mean costs, right? Then we do mean costs. Oh, I haven't defined an cost yet. See, that's what I'm trying to say. This feels just like, yeah, I guess it's fine. Because based on what it is, you will have different results. Right, depending on what it is, you'll have different results. Okay, let's give this a shot. Uh-oh. My bad. Oh, I can just do min cost. I already assigned it. Right, I can just do min cost. There we go. Yeah, that is faster. It is Dijkstra. It's the same as Dijkstra, except you're doing the sorting yourself. They call that a 0-1. Okay, I'm actually interested to see what I did in the past. Oh, I used a hint. I used a hint. Hmm. Oh. Good point. And do we even need this main cost? Well, we need this main cost to ensure this, right? But I feel like all we need is just keep tracking of the cost. Yeah, we just need a cost. I think we just need a cost. We don't even need a main cost. So I think we can even simplify. Further simplifying solution 2. We don't need an array to track the mean costs. We just need one variable, right? We just need one variable. Wait, do we just need one variable? Because we go through all the things, right? And then we reach here, and then we can go to the next, and we will have the current cost, right? The current cost reaching here, and then we pop whoever out, or have the cost of reaching that. Let me think. Yeah, we have the minimum costs as we go through the whole thing, and then we go through the thing, and then we just I don't think we need one variable to keep track of the current mean cost of reaching each cell. Right? Am I crazy? Am I crazy? Oh, hold on. I think you need it. Because you need to compare. Because you don't know if one way of reaching the cell is going to be cheaper compared to the other way. What you have is a local minimum, right? Locally, you go to the cell. You go through many things. You go to the cell. And then you need to compare to the previous. Yeah, we do need it. We do need it. What we might not need, actually, I think, is because we have some steps. Like, do we need this step if it's not equal to? Like, is it possible in this? Like, we hit something twice, basically. We hit something first, right? Because we need to put it in it, and once this one get popped, then we just I think we need that. I think we need everybody. The only thing that we can simplify is here. Yep, I can say if element 1 plus grid nij smaller than minimum costs and index, that is not right. I think this part should come here. Now we do another if here. We can just directly call grid nij. Something like that. I think this will probably make it cleaner. It's the same thing. Okay, it's the same thing. I got this. Oh. I just need to say put a 1. Slightly faster. Okay, that will be it for today. Actually, no, that will not be it for today. I'll see you guys later today, but that will be it for this problem. Alright, I'll see you guys later.